Taufik and my student ID is 20244328686. Today I will explain about the background of study in our experiment. A simple pendulum is a classic example of periodic motion where a small mass attached to a string swings back and forth when displayed slightly from its equilibrium position. According to theory, the oscillation period depends on the pendulum's length and gravity, assuming a small angle and no air resistance, but in real experiment, the measured periods can vary due to random and systematic errors such as reaction time when using a stopwatch or inaccuracies and measuring length. Therefore, statistical methods are needed to analyze repeated measures using average and other measures of location to summarize the data and graph to represent the relationship. This experiment applies statistical analysis to determine whether the observed relationship between pendulum length and oscillation period agrees with theoretical prediction. Our study focuses on understanding the motion of a simple pendulum. The objective of our research are three. 1. To investigate the relationship between pendulum length and oscillation period through experimental measurement. 2. To apply statistical measures to analyze the distribution and consistency of oscillation period data. And 3. To support the theoretical model of a simple pendulum using experimental and statistical analysis.
Hello, my name is Kelvin Maipel and my matrix number is 2024408276. Now I will explain about the significance of study. So, this study shows how statistical analysis can be used to explain the relationship between pendulum length and oscillation period. The findings support basic physics theory and help improve understanding of data analysis and interpretation using statistical tools. Moreover, the study proved practical experience in applying statistics to experimental data, highlighting the connection between physics concept and statistical analysis. This integration also helped to interpret experimental data more effectively, particularly in understanding the relationship between pendulum length and oscillation period. Let's move on to the limitation of study. Although this study is based on the well-established physical principle, several limitations should be considered. Firstly, the accuracy of oscillation period measurement may have been affected by human reaction time during manual timing. Next, external factors such as air resistance and friction at the pivot point could not be full control. The limited range of pendulum length and small sample size may also affect the general stability of the result. Therefore, the data should be interpreted within the experimental condition of the study.
We go to chapter 2, which is methodology. Next, we look at the data description. This report is based on an experiment investigating how the length of a pendulum affects its oscillation period. Different pendulum lengths were measured in centimeters, and the time taken for a fixed number of oscillations was recorded using a stopwatch. The oscillation period was calculated by dividing the total time by the number of oscillations, and the measurements were repeated several times to improve accuracy before calculating the average period of each length. The data consists of paired continuous variables with pendulum length as the independent variable and oscillation period as the dependent variable, allowing correlation and regression analysis to determine the relationship between them and to confirm the theoretical expectation that a longer pendulum has a longer oscillation period. Three graphical techniques, which is histogram, scatter plot, and box plot, were used to analyze how a pendulum length relates to oscillation period in this study. The histogram was used to show how many times each oscillation period occurs. By doing this, the writer can see the general shape of the data and determine if it has a skew shape or contain any outliers. The scatter plot diagram shows the relationship between pendulum length and how it takes an oscillation to occur, and demonstrated how the length of a pendulum will change over time by increasing the length. The scatter plot allows a visual representation of a correlation between the length and period of a simple pendulum. The box plot shows how spread out the oscillation period data for each pendulum length is, with reference to the median, quartiles, and outliers. By utilizing these three graphical methods together, the study created a comprehensive visual analysis of the data in terms of the overall distribution and consistency of the data, as well as the underlying relationships between these two variables. Last but not least, on the chapter 2 is numerical techniques. These techniques are commonly used to organize, summarize, and analyze numerical data. They help in understanding data patterns and supporting decision making in various fields such as education, science, and research. On this slide, several numerical techniques are listed. Number 1, measure of central tendency, which is mode, median, and mean. Number 2, measure of location, which is quartile and interquartile range. 3, measure of dispersion. 4, range. 5, variation and standard deviation. 6, population variance, sample variance, and standard variance. 7, simple standard deviation. 8, measure of skewness. 9, plot and whisker plot. 10, Pearson coefficient of skewness. 11, correlation. 12, regression. 13, coefficient of determination. And 14, fitting and straight line.
Is the data for our case study. Histogram brought two peak shapes simply reflect the wide range of length tested, which is 0.2 meter to 1.5 meter, showing that the data is spread across various oscillation speed rather than clustering around a single. For this histogram is 3.61. For this histogram, instead of a typical bell curve where the most items are medium size, these 15 threads follow a near uniform distribution, which is every length interval from 0.3 to 1.7 contains exactly 2 threads. The only exception is the very first interval 0.1 to 0.3, which has just one thread. As a result, a flat histogram that shows have an equal variety of short, medium, and long threads. For this box plot, the median is 3.6, which is matching the average. And then, because the median line the swings time are eventually balanced, the data spans from 0.8 to 6.1. They are meaning every measurement fit the expected trend. The descriptive statistic, minimum and maximum value for the length of thread are 0.2 and 1.6 respectively. Then the mean and standard deviation calculated for the period squared is 0.9 and 0.4471. Hence, the minimum value period squared is 0.81 and the maximum value is 6.45. Lastly, the mean and standard deviation for period squared are 3.61 and 1.80578. The relationship between length and period square is perfectly linear, evidenced by an R-square value 1.000. The experimental regression equation is y is equal to negative 0.02 plus 4.04x. It reveals that relation coefficient are of 1.000, which indicates a perfect positive correlation. In practical terms, this means that as the length of the thread increases, the square of the period increases in a perfectly predictable linear fashion. This relationship is statistically significant, as evidenced by the p-value being less than 0.001. This value is far below the standard alpha level of 0.05, meaning the probability that this relationship occur by random chance is nearly zero. The sample size for this analysis was 15. The regression analysis revealed that a perfect positive correlation between the two variables is 1.000. The coefficient of determination R square is 1.000, indicates that the pendulum explains 100% of the variance in the square of the pendulum period, meaning that the length of the threads is a perfect predictor of the period squared in this datasheet. The standard error of the estimate was calculated at 0.3523, that demonstrating the observed data deviate negligibly from the regression line. The result shows a nearly perfect connection between the two, which is, in simple terms, the length is the key. The longer the thread, the longer the swing. And for every 1 unit increase in thread length, the squared swing times decrease by about 4.04 units. Matches physics theory almost perfectly. Standardized beta of 1.000 means that the correlation is basically 100. The 0 point as expected. If there is no thread, there is no swing. The model correctly shows the relationship starts at 0.
In conclusion, the statistical analysis of the experimental data show a clear relationship between pendulum length and oscillation period. As the length of the pendulum increase, the time taken for one oscillation also increase, indicating a strong positive relationship between the two variables. This pattern is clearly supported by the graphical analysis as well as the correlation and regression result. These findings are consistent with basic physics theory and demonstrate how statistical method can be effectively used to analyze and interpret data obtained from physics experiments.